Thanks for giving me the opportunity to speak here. Um, my purpose in showing this or going through this material is I guess twofold. One, to give an indication of what on earth a statistician would be doing in the wildfire domain, and the other is to sort of set things up so that some of my students can give you sort of updates on what they've been doing in relation to this previous work that I'm going to be going through. And so this previous work was carried out with a former PhD student, Dongying Wang, and as I said, hopefully it gives you an idea of some of the things that, at least a little bit of uh, some of the things that statisticians can bring to the table. Okay, so after a bit of an introduction, I'm going to talk. I'm going to go away from fire a little, well, quite a bit, and talk about something called local polynomial regression. Getting into some of the technical details of it, hopefully not too much for this audience, and then. And then I'm going to talk about something called data sharpening, which has to do with perturbing data points, and then come back to fire, but not exactly wildfire. Over the last few years, I've been involved with several students and other colleagues in looking at small, like actually tiny fires in a fume hood, actually, and recording the behavior in by video, and then asking questions about what's going on with the fire spread. And segmentation of the videos has been a challenge. And in fact, I'll show you a little bit of the results that came out with Dongying, and then in a future session, one of my current students will actually follow up with some better approaches than what I'm going to show here. I finish off by applying the data sharpening to the time series of RGB channels that come from the videos to come up with um, uh, estimates, or I guess smoothed or filtered uh, um, versions of the videos. And from those, you can do things like bootstrap confidence intervals and things like that. And so I'll show some of that. So the first data set then has nothing to do with fire. It's just an example data set to show the basic technique. You've just got a scatter plot of data, and the idea is, can you fit a smooth curve? And the model that underlies what I'm going to talk about here is just a one-dimensional curve, where yi is the if you go back to this faithful data set, we've got the times, the lengths of the eruption times at Old Faithful, and the waiting time between eruptions. And so so y here would be the eruption time, and x would be the waiting time between eruptions, or before the next eruption. And we assume that epsilon is independent noise with a constant variance, sigma squared, and a mean of 0. And we also assume that the function underlying these data is smooth, even though there's a lot of noise. And so local polynomial regression, if you look at the minimization that's going on here, if you ignore the red parts, then you see that this is just a version of least squares polynomial regression. The red parts have to do with giving weight to observations that are close to a particular point, lowercase x, And H there is what's called the bandwidth, and it controls the amount of smoothing. And the K function, the red function, is a kernel function which controls these weights. Higher weights close to lowercase x, and lower weights further away. And in fact, for some of the kernels, for example, this one called the Epineshnikov kernel, given at the bottom, the weights are actually zero outside a compact interval. The regression is carried out to give you estimates of these beta parameters. Those are the things that are being estimated. And the intercept, beta hat x0, is actually the estimate of the function at lowercase x. And so you carry this out for a set of grid points x, and that gives you a smooth curve, such as what we're seeing here. In this particular case, this is the local constant version, so it's a very simple case where there's actually no extra polynomial terms, just a constant term, just the intercept. And in this case, this is the local linear case, so it's simply an intercept plus a linear term, and this gives you the curve here. Now, the local polynomial regression is a class of estimators that happens to be linear in the responses. And so what that means is the y's are the responses, and so you can write the estimator as a linear combination of the y's, and the coefficients in that linear combination are functionally independent of the y's, and this opens up some possibilities for us to do some simple, well, relatively simple kinds of apply some relatively simple kinds of constraints to the estimates. Okay, so this is just to show that the form of those coefficients for the local constant and local linear cases. So I just mentioned that we could try to constrain these local polynomial regression estimates. And so one possibility would be such as that Old Faithful data set. You might expect that the underlying regression function should be monotonically increasing, or you might expect some kind of convexity to be imposed on the regression function. And so long ago, I worked with an Australian mathematician to come up with what's called constrained data sharpening, which provides one method for imposing such a constraint. The idea that we worked with there was to perturb the data in the smallest possible way, so that the local regression estimate applied to the perturbed data satisfies the constraints at the grid of points that you're doing the estimation on. And so sort of formally, what you do is you remember the yi's are the responses. And so what we're doing here is we're just finding some yi stars, which will be close to the yi's, subject to the constraint that that the derivative of the estimate is non-negative. And so when you apply the estimate to such perturbed y's, you'll get a monotonic increasing regression function. And it turns out that this is a relatively straightforward convex programming problem with linear constraints. And so as long as p is greater than 1, there's actually a unique solution. When p is equal to 1, this is a linear programming problem, and such problems sometimes have multiple solutions. When P is 2, this is a quadratic programming problem, which is very straightforward to solve, even if you have a relatively large data set. So if we apply this technique to the old faithful data set, in the local constant case, we now get a monotone increasing function. And again, in the local linear case, there's again no further up and down bumps, just a monotonic regression. Now, when p is less than 2, the method is usually more accurate, but poses numerical issues. And so Dongying was expert with the Douglas-Ratchford algorithm, which is an optimization approach that can be applied here, and it's stable and efficient. And so she applied this in the one-dimensional case with success, and then in higher dimensional settings, where you would have more than one type of explanatory variable in place of just the waiting times, you would have additional variables, additional predictive variables. You can use backfitting to handle these kinds of additive models. All right, so uh, the additional question though that Dongying and I looked at was, suppose you don't really know beforehand what kind of constraint you really need to impose on the data. And so what she did was she incorporated curve registration to the video images that we're going to talk about, to generate a practical and effective data-driven constraint. Okay, so what I want to show, if this will work, I'm not sure if you can you see the fire? Good. Okay, so this is just an example of one of these fires I was talking about, burning in a fume hood. And what we're watching is wax paper that's being treated with potassium nitrate to keep it from flaming too much. So we're actually just looking at a smoldering fire. One of the reasons that this is of interest to me is that in fact this at a small scale provides a test bed of examples where that there's sort of if you will, a mouse model for what's happening in actual wildfire. If you're looking at aerial photography or satellite imagery of wildfire, these pictures are surprisingly similar. And so here's an attempt at segmenting that fire. Okay, the black, of course, is already burned. The green is unburned, and the red and yellow correspond to where we've got some flaming, or where there's actual combustion. All right. Now we did a similar kind of experiment, but in a darkened lab, so that we could remove some of the effects of smoke. We're only looking at visible spectrum here anyway. So in the dark, the flame, or the little bits of fire can shine through the smoke more clearly. Okay, so that particular video is just a collection of 240 by 320 images, which have RGB channels. And so one of the main things that we want to know is where there's actually fire. And so the red channel was of primary interest, although the other channels are are somewhat important too. But what we see down below are red channel series for three of these pixels. And so the spike, of course, that you see in each of these three pixels corresponds to the time that there was a little bit of flaming in the or at least the fire was passing through the pixel. The rest of the rest of these noisy time series correspond either to well, prior to the spike. That's when there's no fire, and we're just looking at the unburned substrate. You get the spike, and then immediately after the spike, the pixel series drops down to essentially almost to black. And so the goal is to remove that noise and replace everything before the spike by something like green. Then at the spike, you want to have maybe red, and then after the spike, you want to replace this noisy small these noisy small values with black, which is essentially zero. All right, and so then the question with, well, going back to these curves, um, so these are at three different locations. You can see that the spikes occur at different places. They're more or less the same kind of shape. They have different heights. Uh, and so the question is, can we improve, can we use this constrained data sharpening idea to help to remove some of that noise? And so curve registration is useful here, because what we can do then is essentially overlay these spikes on each other, both in terms of their horizontal location, but also scale them in terms of their vertical heights. Okay, and so this provided a way to construct a data-driven constraint for these series, and then with that constraint, we use the data sharpening procedure that I described before, and then uh, um, apply the smoothing, and then so applying the smoothing, then you can get in a sense well, what I like to think of as the perfect fire, because it's then a sequence of images that can be put back together into a video form, where you are looking really at um, where the fire is burning, but with a lot less noise. And then the other thing we can do, though, is we can subtract the resulting curves from the original data and obtain residuals, which can then be used in a form of bootstrap, which I'd be happy to talk with people about at a different time if they're not familiar with the bootstrap. So what I'm going to show you here is going to show you again for this darkened video. That's the supposedly perfect fire. Okay, so that's the smoothed one, and then you can get a 10% confidence limit. It comes up. Is it coming? There it is. Okay, so this, we have to work on the interface a little bit, but this would actually be this. What we're seeing here then is, in a sense, a version of the fire which um, uh, which would be contained by the true fire with probability 90%, and this one should be bigger, and this will contain the true fire with probability 10%. Okay, so in a sense, those are effectively well, I guess 80% confidence intervals, if you will, for the fire. And so that's for the darkened one. So can we do the same kind of thing in that smoky daylight fire? And it turns out that if you subtract the red channel from the green channel, it may be hard for you to see what's going on here, but you'd get something that looks an awful lot like the fire burning in the darkened room. And that's where I'm going to stop.
Great.
Are
Thank you
there any
so
questions
much.
for me?
All right, thank you, John. Questions?
Thank you, John. I have three questions. Maybe I just quickly ask them, and whatever you feel you like them better, you can answer. My first question is, so is this approach invariant to the resolution of the images, in a sense that, like, if you look into one, like, or you design it basically, because I assume some of the parameters you mentioned at the beginning are hyperparameters, which you probably have to look into tuning them for the best performance. And then what happens if you go from one resolution domain to another resolution domain? I might be wrong, but you can just clarify a little bit on that in terms of invariancy to resolution. Then my other question is, I'm just curious, like, why are we looking at the red spectrum during dark time compared to, maybe, in my opinion, maybe something toward closer to a combination of RGB, which is closer to white, might be maybe a better representation of the firework. I'm just thinking out loud. And finally, I'm gonna address the elephant in the room, which is how is this compared to modern machine learning methods, which actually are looking at, like, occlusion or denoising images and so on and so forth, like with data and scale, right? Obviously, I assume the most significant benefit of this is probably doesn't need a lot of data as compared to, let's say, machine learning methods, and maybe provide some interpretability, but just wanted to hear your thoughts on the comparison with machine learning methods. Thank you.
Okay, well, these are all very good questions. The third question I'll address first, because I guess I take issue with modern machine learning methods, because the basic approach that I'm talking about originated in 2001, but it is current, and it is under development, and so in a sense, it's much more modern than machine learning methods, which are really just, generally speaking, badly interpreted statistical methods. My bias is showing, but you are correct that this doesn't require the huge amounts of data that some of the deep learning methods would require. That said, I do have the PhD student who's continuing on with this project is using some deep learning methods to help with the segmentation, and it is working better. But I believe that the future is bright for small data methods. I don't think the future is that bright for deep learning methods. I think the deep learning methods, we're now looking in the rearview mirror, but there's a lot to be done with small data. Okay, sermon over. Now, the first question you asked, which is a really good question. So why did we use red? um, we tried several different combinations, and that just seemed to be the one that provided the best result. But you're probably right that that more work could be done in terms of uh, optimizing that. Because I mean, this was that part was very informally or subjectively decided upon. In terms of, well, I guess that was your second question. Your first question was the about the resolution. Another really good question, and uh, the the videos that we've been looking at are all at the same resolution. So unfortunately, I can't. I would be kind of taking a strip off of your president's playbook if I gave you a definitive answer, because it would be completely made up. Um, but speculating uh, a little bit, I think that the resolution won't really make a big difference. However, actually your question had several components to it. The big component, or actually, it's the little component. That that bandwidth, that's a critical parameter, and that one may or may not be. I wouldn't want to prejudge whether that's connected to the resolution. But the resolution itself has other interesting connections when I didn't talk about actually stochastically modeling the fire, which is another thing that I've been looking at. Resolution plays a surprising role in how a mechanistic fire growth model actually can be developed. I want to actually just make one further comment because it just occurred to me in relation to the third question you asked. In these videos, we of course, or in this context, we sort of have control over almost everything, and so we can produce as many video frames really as you want, like 10, 15 per second or even more. Whereas when you actually start looking at satellite imagery, you're looking maybe at one per day, if you're lucky. So the amount of data that you're actually going to have in practice is going to be much more limited. And of course, the substrate is going to be much more heterogeneous than what we're looking at here. Although the potassium nitrate does play a nice role in making, in sort of providing a not bad heterogeneous kind of environment for the fire.
Thank
In
you.
fact, actually, another student of mine, another former student of mine, in his PhD thesis, he actually looked at some electron microscope images of the treated wax paper, and it looks a lot like slash, uh, which is kind of interesting. So at a microscopic level, these things actually do look um, like like real forest landscapes that have been kind of badly logged.
Excellent. Thank you, John. I appreciate it.
Oh, okay. Oh, there's some chat. I don't know. Is there a publication? It's taking a little while to come out. Dongying and I are getting back to work on this. She graduated a while back and has been working for an insurance company, and so has been distracted. But we are her thesis could be provided. It's got a chapter on it. Let's see. AI generated.
Yeah, is there any other questions for John?
I can go ahead with another question if there's.
Oh, yeah, sure, because we have time.
So John, do you think this can help with because I mean, I think another advantage talking about our machine learning is I think it gives some interpretability into the movement, the progression of the time series, looking at the parameters that you basically feed through the data. So do you think this can be used for forecasting the progression of the like wildfire movement as well, just looking at how the parameters are learned as compared to, let's say, machine learning, which would be kind of like a black box, right?
Right. Yeah. Yeah. In fact, actually, that is what I'm hoping, and that's one of the reasons for cooking up these confidence limits as well, because you're exactly right that if you can model these pixel time series properly, then as long as you're continuing through the same kinds of substrate, then yes, you can. Well, all the conditions have to be the same. One thing to remember here is that there is no ambient wind speed, and of course that's going to control the rate of spread very much. But yes, you're going to be able to track these time series through the pixels, and of course, then you could extrapolate further, and by incorporating the confidence limits, you can kind of give yourself an idea of how the uncertainty is increasing over time. So yes, that is a goal.
Excellent, thank you.
You're in Calgary.
Who, me?
Yes.
Yeah, I am.
Oh, okay. Okay. Yeah, I'll come and I'd like to come and visit you sometime then and talk
Of
more about
course.
it. Yes,
We'd
you're
be
not
happy
far
to
away.
host you anytime. Yeah. Let's connect offline. I would be glad to bring you over for sure.
Yes.
So there's another question in the chat from Fatme. Fatme, how does this computation method compare to Bayesian methods for prediction fire spread?
Okay. And that's a good question, and I really don't have the answer for that one because I have not tried. That doesn't mean that it shouldn't be tried. I am I am a what is it? An agnostic Bayesian. I really only do frequentist methods, but it's not because I'm opposed to Bayesian methods. It's because I am not good enough to do them. So I would encourage people to think about how to do this from a Bayesian perspective, because I do think that there's potential there. The other question is, what are the computational limits? Have you used any external data for the prediction? Not here. We have tried some of our other modeling approaches. We have tried to use external data, but we haven't moved to that step for this particular type of problem yet. But that's an important next step.